Good day, everyone. Now we need to learn how to interpret computer regression output. So we don't have some of the programs that are mentioned in our book, but we do need to know how to read them. Our book uses the same ones they display on the AP exam, but a number of statistical software packages produce similar regression output. So we need to be sure that whatever program they use or however they display it, you can locate the slope, which is usually B, the y-intercept, which is usually A, and the values of s and r squared. So here's one from a program called Minitab. Okay, so where it says coefficient, that's really where our slope and our y-intercept are going to come from. The constant, if you think about it, the y-intercept is a constant. And then this represents the variable. They're using the example about, I think it was non-exercise activity change. So that's just what that stands for. So under coefficient, what's next to constant is the y-intercept. What's next to whatever variable, so this name will change problem to problem because this represents whatever the variable is for x. That coefficient is our slope. And then not too difficult to find s because it says s equals. And that tells us the standard deviation of the residuals. And not too hard either to see r squared because that's r dash clearly r squared. Okay, here's another program that's showing the same information, showing r squared. Now here it doesn't directly say s. You've got to remember the root mean square error goes with s. Root mean square error. And then this part's pretty similar. The estimate for the intercept and what's next to the variable is the estimate for the slope. So it's all the same numbers, but you got to make sure you know where to look in different kinds of programs. Okay, let's talk about interpreting regression output. So how well does the number of beers a person drinks predict his or her blood alcohol content? 16 volunteers with an initial blood alcohol content of 0 drank a randomly assigned number of cans of beer. 30 minutes later, a police officer measured their BAC. Least squares regression was performed on the data. A scatter plot with a regression line added, a residual plot, and some computer output from the regression are shown below. So I'd be discussing this if we were in class together to basically say, why might this be different for different ones? Well, in short, based on your body size, this can affect how much one beer affects your blood alcohol content, also how quick your metabolism is, or even how much you have had to drink in the past. Which, since you're all under 21, you know that should be 0. So here's the output. So we're going to look at how to read this. So we can look and see that down here under coefficient, we have the y value, or the y-intercept, negative 0.0127, and our slope right here, the coefficient next to beers, since beers is our x value, number of beers they consumed. We also see s up here, 0.0204, that seems pretty small, r squared of 80%, which is decent. So what is the equation of the least squares regression line that describes the relationship between beers consumed and blood alcohol content? As always, define any variables you use. So we'll have y hat equals, then we saw in the previous slide, this y-intercept and this slope. And we defined x is the number of beers consumed and y is the blood alcohol content. So another way you could write it is instead of writing y hat, write blood alcohol content equals same numbers, and you could put number of beers in instead of x. So then interpret the slope of the regression line in context. So this slope says that for every additional beer consumed, the least squares line predicts an increase of about 0.018 in blood alcohol content. So as our x value increases by 1, our y value increases by about 0.018. Now it says to find the correlation. So to find the correlation, remember that's r, we take the square root of r squared, because r was not given to us in that output, but r squared was. So we just take the square root of it. We do have to include plus or minus when we take a square root of a number, but since the scatter plot shows a positive direction, we can also think since our slope is positive, that tells us it'd be in a positive direction, we'll stick with the positive r value. Just a quick reminder, r, we like it to be close to positive 1 or negative 1. It doesn't, as far as how good it is, it just matters how close it is to either one of those. But we want to use the one that makes the most sense with the direction of the data and the slope we found. So we use the positive 0.894. So is a line an appropriate model to use for these data? What information tells you this? So while in this class we are just using linear regression, things that statisticians have to decide is, okay, is a line really the best fit for this? Or should we use something curved or something logarithmic or different things like that? So we decide a line does seem to be appropriate. There's lots of different reasons we can say this. First of all, if you do a residual plot, you would see a fairly random scatter of points about the horizontal line representing the prediction error equaling 0. The residuals are all between negative 0.03 and 0.03, except for the subject who drank 9 beers. On average, predictions, that's a lot of beers, oh my goodness. On average, predictions of blood alcohol content using the regression line would be off by about 0.02 for the 16 people in the study. We know that from the S value. Now that may be too much prediction error because the legal limit for blood alcohol content is 0.08. So I think I mentioned in the previous video for earlier in the lesson that one thing you have to consider as far as size of residuals and things like S is how big your actual data is. So since the legal limit is 0.08, we're talking small numbers that we're dealing with. S being 0.02, I mean, that's a quarter of what the legal limit is. And 0.03, those are actually a little bigger than they may first appear, considering the level of data we're talking about. These are all relatively small values in the Y. But moving on, based on the value of R squared, 80% of the variation in the subject's blood alcohol content readings is accounted for by the least squares regression line of beers consumed on the BAC. So the residuals are fairly small, S is somewhat small, and R squared tells us 80% of the variation is accounted for. So all those point us to saying, yes, a line does seem to be appropriate. And then E, what was the blood alcohol content reading for the person who consumed 9 beers? Show your work. So based on the linear regression, the line we were given, we just plug in 9 for X because X is the number of beers consumed, and we get an extremely high blood alcohol content of 0.149. So that's nearly double the legal limit. That is way too much. So from the residual plot, the subject's residual is about 0.045. Since the residual equals the observed minus the predicted, we can actually figure out what the observed one was. So I need to back up because I don't think I explained the process we're doing in this very well. They asked what was the blood alcohol content reading for the person who consumed 9 beers. So what they're really asking for is what was the observed amount. Well, we were not told that. They did not give us an XY chart or data to specifically say how much each person received. But we can figure that out because we know the residual, look right here, the residual is the observed, which is what we're looking for, minus the predicted. So since we can get the residual from the residual plot, we can get the predicted from the actual equation we were given. That's what we did up here in this blue spot. We can then plug those two in, which you see right here, and solve for the observed y. So that's 0.194, which was a very, very large blood alcohol content. So there are times you'll have to use this formula, residual equals observed minus expected, or observed minus predicted, whichever one you want to say, to solve for one of them. There are times they may give you these two, observed and predicted, and you solve for the residual. There may be times they give you the residual and one of these on this side to solve for the other. Correlation and regression wisdom. Yes, wisdom is important. Correlation and regression are powerful tools for describing the relationship between two variables, but you should be aware of their limitations. So like we've talked about, statisticians like to lie. They like to finagle the data in such a way that makes it sound like what they want it to sound like. So the distinction between explanatory and response variables is important in regression. We've got to make sure we correctly choose which one's the x value, the explanatory, and which one's the y value, the response variable. That does matter. So you can see the differences we have there. The r-squareds are the same. It actually doesn't affect r squared at all. It's 60.6% in both. But it changes our equations rather significantly. You can see these up top. Also changes our s rather significantly. And that's because we're dealing with different levels of data. Meaning the fat gain, we're only looking like 0 to 4 range. That's why these are pretty small, because our y values only range from 0 to 4. Whereas if this is our y value, it ranges from negative 100 to positive 700, making these numbers in the equation and the s much bigger. Correlation and regression lines describe only linear relationships. So let me just go back there. Correlation, R, and a regression line should only be used to describe linear relationships. These do not apply to curved lines of any kind, whether it's quadratic, cubic, quartic, logarithmic, exponential, any of that stuff. Correlation and regression are only used for linear relationships. Correlation and least squares regression lines are not resistant. We previously talked about how outliers can have a pretty strong effect on the line. It doesn't matter if it's an outlier in the y sense, which is what child 19 in this picture would be, or in the x sense. This isn't that far off the line, but it is skewing the line significantly because it is so far away from these as far as the x variable is concerned. So correlation and least squares regression lines are not resistant. So this is showing how we get very different results based on taking away the outliers. So I believe the line we see in the middle is the one that is including both child 18 and child 19. Okay, if we take away child 19, it does lower us a little bit, it changes it. If we take away child 18, it significantly changes it. Like I said, I can't remember if we did this before or not, but regardless, it turns out that outliers in the x sense, in the left and right direction, typically have a stronger pull, stronger change on the line in its equation than one in the y value in the y sense. So an outlier is an observation that lies outside the overall pattern of the other observations. Points that are outliers in the y direction but not the x direction, that'd be child 19, have large residuals. So points that are outliers in the y direction but not the x direction of a scatter plot have large residuals. Other outliers may not have large residuals. So child 18 is not going to have a very large residual. You see it's relatively close to that line in the center. So child 18 does not have a huge effect on the residuals, but it does have a huge effect on the equation of the line. Child 19 has a huge residual, but has less of an effect on the equation of the line. An observation is influential for a statistical calculation if removing it would markedly change the result of the calculation. Points that are outliers in the x direction of a scatter plot are often influential for the least squares regression line. So that's a more formal way of what I was trying to point out here. So child 19 does affect the residuals, but because it's an outlier in the y direction, it's not very influential. It doesn't change the equation of the line a whole lot. Child 18 has a relatively small residual, but because it's an outlier in the x direction, it is very influential in changing what the equation of the line would be. Association does not imply causation. In all seriousness, if you remember nothing else from this course, I think this is worth it the most. Association does not imply causation. Just because two variables are related, that does not necessarily mean one causes the other. For one thing, it may be there's something else involved, something that we're not measuring that's causing both of them. It could be that we mix up which one causes which. So just because two things are associated does not imply one causes the other. So an association between an explanatory variable x and a response variable y, even if it is very strong, is not by itself good evidence that changes in x actually causes change in y. So a serious study once found that people with 2 cars live longer than people who only own 1 car. Owning 3 cars is even better for people's lifespan, and so on. So there is a substantial positive correlation between the number of cars, x, and the length of life, y. And then the question, why? So we don't really think buying a car all by itself is going to make you live any longer. The association being strong here, the correlation, is likely to do with another variable, and that's to do with money. People who are wealthier tend to buy more vehicles, and people who are wealthier also tend to have more money for health care. They often have more money to buy better quality food. They often have more money to be able to visit the doctor more often and take care of health problems when they have them. So while there is a strong correlation, a strong association between the number of cars someone owns and their lifespan, neither of those is causing the other. Something separate is. So a strong association or correlation is not by itself good evidence of causation. And there's your homework to talk about interpreting these things and about using wisdom with correlation and linear regression. I wish you well.